네, 안녕하세요, 여러분. 인공지능과 법 제9강을 시작하겠습니다. 네, 9강은 주제는 인공지능과 의사결정입니다. 네, 우리 9강에 앞서서 우리 지난 시간 복습을 해보도록 하겠습니다. 우리 지난 시간에는 초연결 사회에 대해서 배웠죠. 그래서 초연결 사회 어, 가 이제 미래 사회의 한 모습일 것이다라고 하면서 그것과 관련된 여러 가지 이론적 배경들을 살펴볼 수 있었습니다. 예컨대 뭐 동조화 현상이라든지 카오스 이론, 나비 효과, 뭐 degrees of separation, 또 공진 현상 등과 같은 그런 개념들을 배웠습니다. 실제 사례도 봤고요. 그래서 이제 미래 사회가 초연결 사회가 된다 그러면 이제 그 사회에서 법은 어떻게 이제 작동을 하는 것이 옳은가라는 것을 좀 음미해 보는 시간도 가졌는데요. 그래서 초연결 사회가 된다는 것은 이제 인간과 그리고 인간을 둘러싼 환경 그리고 우리가 이제 흔히 이제 객체로서 쓰는 그런 도구로 쓰는 이제 기계들 이런 것들이 이제 하나가 된다는 거죠. 연결돼 있다는 거죠. 그래서 이 기계가 어찌 보면 이제 센서를 통해서 우리의 움직임을 이해하고 또 그래서 이제 이렇게 된다는 것인데요. 그 기계 중에서도 이제 생각하는 기계, 즉 말하자면 스마트 기계가 나타난다는 거죠. 이제 그게 바로 이제 어떤 우리가 만든 인공적으로 만든 똑똑한 지능, 즉 인공지능이라고 할 수 있겠습니다. 그래서 특히 이제 인간과 기계, 인공지능과의 관계를 생각했을 때 공존 가능한 경우는 이제 어떻게 해야 되는 것인가라는 것이 좀 우리한테는 주어진 어떤 법적 과제라고 할 수 있겠습니다. 자, 그럼 본격적으로 이번 시간에는 그 똑똑한 기계, 즉 인공지능에 대해서 알아보도록 하는 시간을 가질 텐데요. 인공지능 기술이 어떻게 나타나게 되었고, 어, 이제 거기에 대한 이제 개념적인 어떤 역사적인 어떤 배경을 좀 살펴보는 그런 시간을 먼저 갖도록 하겠습니다. 여기에 영어로 약자로 되어 있는 부분들이 있는데요. 뭐 DM이라든지 BD, ML과 같은 그런 약자가 보입니다. 자, 여러분들 이게 무슨 뜻인지 한번 같이 정리를 해보도록 할까요? DM이라 그러면 데이터 마이닝, 데이터를 채굴하는 것, 이런 걸 말하는 것이고요. 그리고 BD라 그러면 그 큰 데이터, 즉 빅데이터를 이야기합니다. 그리고 ML이라 그러면 머신이죠. 머신 러닝, 즉 기계 학습을 ML이라고 부르는데요. 좀 이런 이제 약자에도 여러분들이 좀, 좀 친근해지면 좋을 것 같습니다. 그리고 인공지능이 최근에 이제 2022년 이후부터 뭐챗 GPT 같은 게 나타났잖아요. 그래서 이제 그걸 좀 구분하기 시작합니다. 그래서 기존의 AI와 그리고 챗GPT 같은 생성형 AI를 좀 구분해서 보는 것들, 그걸 먼저 살펴볼 것이고요. 그런 다음에 인공지능을 둘러싼 법적 쟁점으로서의 뭐 AI 윤리라든지 또는 뭐 책임의 기속 문제, 누가 책임질 거냐, 그다음에 AI가 만든 어떤 결과물들에 대한 어떤 저작권 또는 생성 과정에서의 저작권 이런 것도 있을 수 있겠죠. 또 그리고 그 인공지능이 기본적으로 어떤 사람들의 어떤 정보, 개인정보라든지 또는 프라이버시를 좀 침해할 우려가 있다. 또 인공지능이 만드는 과정에서 알고리즘을 우리가 운용을 하는데요. 그 알고리즘에 대한 어떤 규제, 왜냐하면 편향성이 있기 때문에 뭐 이런 것들을 살펴볼 것이고요. 자, 우리 이제 미래 사회에서 인공지능이 가져다 줄 많은 문제점, 우리의 의사결정을 이제 보조하는 수단으로서 또는 의사결정을 뭐 많은 부분 맡기기도 하겠죠. 여러분 SF 영화에도 보면 사실 이제 인간이 들어가기 힘든데 뭐 아니면 뭐 여러분들이 뭐 비행기를 타더라도 뭐 자동 항법 장치 이런 것들을 둘 때 약간 이제 그런 기계의 도움을 많이 받는다는 거죠. 그랬을 때 이 미래 사회가 정말 합리적으로 의사결정을 하게 되면 유토피아가 될 수 있지만 그렇지 않고 뭐 불합리하게 또는 어떤 부당하게 의사결정을 한다 그러면 이제 디스토피아가 될 수도 있다는 말이죠. 그랬을 때 우리는 이제 이 두 가지 중에 유토피아하고 디스토피아 중에서 뭐 좀 좋은 쪽으로 가야 되지 않을까요? 유토피아를 만들려고 할 때 꼭 필요한 것들이 우리 인간 스스로의 집단지성 또는 집단적 창의성이 필요하다는 이야기를 그렇게 이제 결론 부분에 제가 제시를 하면서 이 강의를 하도록 하겠습니다. 자, 인공지능의 개념을 먼저 살펴보도록 하겠습니다. 인공지능은 영어로는 Artificial Intelligence라고 부릅니다. 그 뜻은 인간이 만든 인공적인 지능이다. 이렇게 볼 수 있겠죠. 자, 이라는 개념을 만든 사람은 누굴까요? 인공지능의 아버지는 누굴까요? 여러분들이 이제 음악의 아버지 바하죠. 음악의 어머니 뭐 핸델 맞나요? 그래서 저는 음악 시간에 가끔 헷갈렸어요. 왜냐하면 음악의 아버지 바하는 남자인 것 같고, 근데 음악의 어머니 핸델도 이렇게 가발을 막 하고 있기 때문에 여자인가? 이렇게 생각했는데 핸델도 남자라고 하더라고요. 그만큼 이제 중요한 분들이다. 아버지, 어머니. 자, 인공지능의 아버지는 누구냐면 튜링이라는 사람입니다. 앨런 튜링이라는 분인데요. 자, 튜링이 언제적 사람이냐면 2차 세계대전 당시에 영국에서 활동했던 과학자입니다. 이 튜링이라는 사람이 어, 인간과 비슷하게 생각하고 행동하는 그런 기계가 있지 않을까? 라고 생각을 하고 그 기계를 만들어 보려고 했습니다. 실제로 그렇게 기계를 만들었고요. 그랬을 때 그 기계가 이게 인간처럼 행동하는 거잖아요. 그러면 인간, 진짜 인간인지 아니면 인간처럼 행동하는 기계인지 테스트하는 것이 튜링 테스트라고 하는 것도 있어요. 여러분들이 아마 그 뭐 그런 거 있지 않습니까? 이렇게 뭐 인터넷 같은 거 하다 보면, 당신이 사람이냐라고 했을 때, 뭐 약간 알록달록한 어떤 숫자를, 그죠? 거기에, 어, 넣는다든지 아니면 다음 중에서 뭐 자동차와 관련된 어떤 그림을 찾아봐라. 막 이런 것들이 있지 않아요? 뭐 그런 것들이 튜링 테스트의 일종이라고 볼 수도 있어요. 그러니까 인간이냐 아니면 인간처럼 행동하는 기계냐라는 것을 판단하는 기준. 근데 제가 하고 싶은 얘기는 인공지능이라는 개념 자체는 2차 세계대전 당시에 영국의 튜링이라는 과학자가 처음에 시작했다. 자, 그리고 이제 그러면 이제 인공지능으로 이제 만들어진 어떤 이제 기계가 나오기까지 중간 단계가 뭐냐면 컴퓨터라는 게 있어요, 사실은. 컴퓨터라고 하는 것은 계산하는 기계를 말하는 거예요. 그래서 이제 컴퓨터 사이언스가 이제 컴퓨터 과학이라고 하는 전공인데요. 거기에서는 뭐라고 이야기를 하냐면, 이제 컴퓨터가 계속 이제 발달을 하게 되면 결국에는 인공지능으로 가긴 갈 텐데, 그랬을 때 인공지능이라는 것은 합리적인 생각과 합리적인 행위를 할 수 있는 기계를 만드는 것이다. 이게 이때 합리성이라는 건 사실은 인간만이 가진다라는 것을 전제로 깔고 있죠. 그러면서 이제 컴퓨터 과학자들 중에서 1956년에 존 메카시라는 사람이 다트머스 회의에서 인공지능을 정의를 합니다. 뭐라고 하냐면 지능형 기계를 만드는 과학 또는 공학이라고 정의를 합니다. 그러니까 지능형 기계라면 똑똑한 기계를 말하는 거겠죠. 그리고 1959년에 아서 사무엘이라는 사람이 인공지능의 핵심 분야로서 뭘 정립을 하냐면 기계학습이라는 것을 정립을 합니다. 그러니까 머신러닝이 이제 만든 사람은 누구냐? 아서 사무엘이라는 사람입니다. 그래서 여러분들 좀 정리를 해보자면 음, 어, 이렇게 볼 수 있어요. 튜링이 인공지능의 아버지다. 그 다음에 기계학습, 머신러닝의 아버지는 누구다? 아서 사무엘이다. 이렇게 여러분들이 정리를 해 둘 수 있겠습니다. 그래서 명시적인 프로그래밍 없이도 컴퓨터가 스스로 학습할 수 있도록. 그러니까 제가 아까 얘기했잖아요. 컴퓨터가 계속 진화를 하게 되면 결국에는 인공지능이 될 거고 그 중간 단계가 뭐냐면 기계학습이라고 하는 과정이 있다라는 거죠. 기계학습을 통해서 컴퓨터가 스스로 학습을 하게 되면 이제 그러면 이제 인공지능으로 가는 길이 된다라는 거죠. 그래서 정리를 하자면 인공지능은 인간의 지능적인 행위, 즉 인간의 똑똑한 행위 중에서 가장 대표적인 게 뭘까요? 의사결정이죠. 그래서 이 강의 제목이 인공지능과 의사결정인 거예요. 그리고 의사결정과 비슷한 것들이 뭐가 있죠? 예를 들어서 판단한다든지 추론한다든지 또는 예측한다든지 이런 것들을 컴퓨터가 수행하도록 만드는 기술 또는 이를 연구하는 학문 분야를 인공지능이라고 한다라는 거죠. 네, 이렇게 해서 이제 인공지능에 대한 이제 개념을 좀 살펴봤는데요. 자, 또 나 보겠습니다. 그리고 이제 영상이 하나 있어요. 그래서 어떻게 컴퓨터가 어, 이렇게 창의적으로 되는 것을 배웠냐라는 것을 보는 건데요. 자, 컴퓨터라고 하는 것을 여기 좀 정리를 하겠습니다. 그 영어의 컴퓨트라는 동사가 있죠. 이게 뭘까요? 컴퓨터라는 말은 계산하다라고 하는 뜻이죠. 그래서 그러면 계산하는 사람, 이걸 뭐라고 할까요? 컴퓨터라고 합니다. 그래서 여러분들이 지금은 이렇게 쓰잖아요. 이게 그 계산하는 사람이 원래 그런 뜻이었고요. 사람이고 또 계산하는 계산기, 계산기를 컴퓨터라고 합니다. 그래서 여기서 이제 진화가 되면 이제 결국에는 이제 인공지능이 나오는데 그 인공지능이라고 하는 것이 나오기까지 많은 것들이 있죠. 그래서 빅데이터라든지 또는 뭐 기계학습이라든지 이런 걸 거쳐서 이제 인공지능으로 가는데 그럴 때 빅데이터도 데이터를 어떻게 해야 돼요? 일단은 채굴해야 되겠죠. 그래서 이 3단계가 필요하다는 거죠. 그래서 데이터 채굴, 데이터 마이닝이라고 하면 마이닝이라고 하면 이렇게 광산에서 캐는 걸 말하는 거죠. 그다음에 빅데이터. 그래서 BD, 빅데이터, 큰 데이터, 방대한 데이터. 세 번째로 이제 머신러닝, 즉 기계 학습. 기계가 스스로 학습한다는 거죠. 근데 예전에 컴퓨터는 스스로 학습하지는 않았어요. 그죠? 이제 그 과정을 이 영상에서 좀 설명을 해볼 거예요. 자, 같이 한번 보도록 하겠습니다.
So I lead a team at Google that works on machine intelligence. In other words, the engineering discipline of making computers and devices able to do some of the things that brains do. And this makes us interested in real brains and neuroscience as well, and especially interested in the things that our brains do that are still far superior to the performance of computers. Historically, one of those areas has been perception, the process by which things out there in the world, sounds and images, can turn into concepts in the mind. This is essential for our own brains, and it's also pretty useful on a computer. The machine perception algorithms, for example, that our team makes are what enable your pictures on Google Photos to become searchable based on what's in them. The flip side of perception is creativity, turning a concept into something out there into the world. So over the past year, our work on machine perception has also unexpectedly connected with the world of machine creativity and machine art. I think that Michelangelo had a penetrating insight into this dual relationship between perception and creativity. This is a famous quote of his: "Every block of stone has a statue inside of it, and the job of the sculptor is to discover it." So I think that what Michelangelo was getting at is that we create by perceiving, and that perception itself is an act of imagination and is the stuff of creativity. The organ that does all of the thinking and perceiving and imagining, of course, is the brain. And I'd like to begin with a brief bit of history about what we know about brains. Because unlike, say, the heart or the intestines, you really can't say very much about a brain by just looking at it, at least with the naked eye. The early anatomists who looked at brains gave the superficial structures of this thing all kinds of fanciful names, like hippocampus, meaning little shrimp. But of course, that sort of thing doesn't tell us very much about what's actually going on inside. The first person who I think really developed some kind of insight into what was going on in the brain was the great Spanish neuroanatomist Santiago Ramón y Cajal in the 19th century, who used microscopy and special stains that could selectively fill in or render in very high contrast the individual cells in the brain in order to start to understand their morphologies. And these are the kinds of drawings that he made of neurons in the 19th century. This is from a bird brain. And you see this incredible variety of different sorts of cells. Even the cellular theory itself was quite new at this point. And these structures, these cells that have these arborizations, these branches that can go very, very long distances, this was very novel at the time. They're reminiscent, of course, of wires. That might have been obvious to some people in the 19th century. The revolutions of wiring and electricity were just getting underway. But in many ways, these microanatomical drawings of Ramón y Cajal's, like this one, they're still in some ways unsurpassed. We are still, more than a century later, trying to finish the job that Ramón y Cajal started. These are raw data from our collaborators at the Max Planck Institute of Neuroscience. And what our collaborators have done is to image little pieces of brain tissue. The entire sample here is about 1 cubic millimeter in size, and I'm showing you a very, very small piece of it here. That bar on the left is about 1 micron. The structures that you see are mitochondria that are the size of bacteria. And these are consecutive slices through this very, very tiny block of tissue. Just for comparison's sake, the diameter of an average strand of hair is about 100 microns. So we're looking at something much, much smaller than a single strand of hair. And from these kinds of serial electron microscopy slices, one can start to make reconstructions in 3D of neurons that look like these. So these are sort of in the same style as Ramon y Cajal, only a few neurons lit up, because otherwise we wouldn't be able to see anything here. So it would be so crowded, so full of structure, of wiring all connecting one neuron to another. So Ramon y Cajal was a little bit ahead of his time, and progress on understanding the brain proceeded slowly over the next few decades. But we knew that neurons used electricity, and by World War II, our technology was advanced enough to start doing real electrical experiments on live neurons to better understand how they worked. And this was the very same time when computers were being invented, very much based on the idea of modeling the brain, of intelligent machinery, as Alan Turing called it, one of the fathers of computer science. Warren McCulloch and Walter Pitts looked at Ramon y Cajal's drawing of visual cortex, which I'm showing here. And this is the cortex that processes imagery that comes from the eye. And for them, this looked like a circuit diagram. So there are a lot of details in McCulloch and Pitts' circuit diagram that are not quite right, but this basic idea that visual cortex works like a series of computational elements that pass information one to the next in a cascade is essentially correct. So let's talk for a moment about what a model for processing visual information would need to do. The basic task of perception is to take an image like this one and say, that's a bird, all right? Which is a very simple thing for us to do with our brains, but you should all understand that for a computer, this was pretty much impossible just a few years ago. The classical computing paradigm is not one in which this task is easy to do. So what's going on between the pixels, between the image of the bird and the word bird, is essentially a set of neurons connected to each other in a neural network, as I'm diagramming here. And this neural network could be biological inside our visual cortices, or nowadays we start to have the capability to model such neural networks on the computer. And I'll show you what that actually looks like. So the pixels you can think about as a first layer of neurons, and that's in fact how it works in the eye. That's the neurons in the retina. And those feed forward into one layer after another layer after another layer of neurons, all connected by synapses of different weights. The behavior of this network is characterized by the strengths of all of those synapses. Those characterize the computational properties of this network. And at the end of the day, you have a neuron or a small group of neurons that light up saying bird. Now, I'm going to represent those three things, the input pixels and the synapses in the neural network, and bird, the output, by three variables, x, w, and y. There are maybe a million or so x's, a million pixels in that image. There are billions or trillions of w's, which represent the weights of all of these synapses in the neural network. And there's a very small number of y's, of outputs that network has. Bird is only 4 letters, right? So let's pretend that this is just a simple formula, x times w equals y. I'm putting the times in scare quotes because what's really going on there, of course, is a very complicated series of mathematical operations. That's one equation. There are 3 variables. And we all know that if you have one equation, you can solve for one variable by knowing the other 2 things. So the problem of inference, that is figuring out that the picture of the bird is a bird, is this one. It's where y is the unknown and w and x are known. You know the neural network, you know the pixels, and as you can see, that's actually a relatively straightforward problem. You multiply 2 times 3 and you're done. I'll show you an artificial neural network that we've built recently doing exactly that. So this is running in real time on a mobile phone, and that's, of course, amazing in its own right that mobile phones can do so many billions and trillions of operations per second. So what you're looking at is a phone looking at one after another picture of a bird, and actually not only saying, yes, it's a bird, but identifying the species of bird with a network of this sort. So in that picture, the X and the W are known, and the Y is the unknown. I'm glossing over the very difficult part, of course, which is how on earth do we figure out the W, the brain that can do such a thing? How would we ever learn such a model? So this process of learning, of solving for W, if we were doing this with the simple equation in which we think about these as numbers, we know exactly how to do that. 6 equals 2 times W, well, we divide by 2, and we're done. The problem is with this operator, right? So division, we've used division because it's the inverse to multiplication, but as I've just said, the multiplication is a bit of a lie here, right? This is a very, very complicated, very nonlinear operation. It has no inverse. So we have to figure out a way to solve the equation without a division operator. And the way to do that is fairly straightforward. You just say, well, let's play a little algebra trick and move the 6 over to the right-hand side of the equation. Now we're still using multiplication. And that 0, let's think about it as an error. In other words, if we've solved for W the right way, then the error will be 0. And if we haven't gotten it quite right, the error will be greater than 0. So now we can just take guesses to minimize the error. And that's the sort of thing that computers are very good at, right? So we can take an initial guess. What if W is 0? Well, then the error is 6. What if W is 1? The error is 4. And then the computer can sort of play Marco Polo and drive down the error close to 0. And as it does that, it's getting successive approximations to W. And typically it never quite gets there, all right? But after about a dozen steps, we're up to W equals 2.999, which is close enough. And this is the learning process. So remember that what's been going on here is that we've been taking a lot of known X's and known Y's and solving for the W in the middle through an iterative process. And this is exactly the same way that we do our own learning. We have many, many images as babies, and we get told this is a bird, this is not a bird. And over time, through iteration, we solve for W, we solve for those neuronal connections. So now we've held X and W fixed to solve for Y. That's everyday fast perception. We figured out how we can solve for W. That's learning, which is a lot harder because we need to do error minimization using a lot of training examples. And about a year ago, Alex Morvintsev on our team, he decided to experiment with what happens if we try solving for X, given a known W and a known Y. In other words, you know that it's a bird, and you already have your neural network that you've trained on birds, but what is the picture of a bird? So it turns out that by using exactly the same error minimization procedure, one can do that with the network trained to recognize birds, and the result turns out to be a picture of birds. So this is a picture of birds generated entirely by a neural network that was trained to recognize birds, just by solving for X rather than solving for Y, and doing that iteratively. Here's another fun example. This was a work made by Mike Tyka in our group, which he calls Animal Parade, and reminds me a little bit of William Kentridge's artworks, in which he makes sketches, rubs them out, makes sketches, rubs them out, and creates a movie this way. And in this case, what Mike is doing is varying Y over the space of different animals in a network designed to recognize and distinguish different animals from each other. And you get this kind of strange Escher-like morph from one animal to another.
계획은 전까지 작성해야 되는데.
네. 너 책 뭐 있어?
Here, he's tried reducing, he and Alex together have tried reducing the Y's to a space of only 2 dimensions, and thereby making a map out of the space of all things recognized by this network, and then doing this kind of synthesis or generation of imagery over that entire surface, varying Y over the surface, so that you make a kind of map, a visual map of all of the things the network knows how to recognize. The animals are all here. Armadillo is right in that spot. You can do this with other kinds of networks as well. So this is a network designed to recognize faces, to distinguish one face from another. And here we're putting in a Y that says me, my own face parameters. And when this thing solves for X, it generates this rather crazy kind of cubist, surreal, psychedelic picture of me from multiple points of view at once. And the reason it looks like multiple points of view at once is because That network is designed to get rid of the ambiguity of a face being in one pose or another pose, being looked at with one kind of lighting, another kind of lighting. So when you do this sort of reconstruction, if you don't use some sort of guide image or guide statistics, then you'll get a sort of confusion of different points of view because it's ambiguous. This is what happens if Alex uses his own face as a guide image during that optimization process to reconstruct my own face. So you can see it's not perfect. There's still quite a lot of work to do on how we optimize that optimization process, but you start to get something more like a coherent face, rendered using my own face as a guide. You don't have to start with a blank canvas or with white noise. When you're solving for X, you can begin with an X that is itself already some other image. That's what this little demonstration is. So this is a network that is designed to categorize all sorts of different objects, man-made structures, animals. And here we're starting with just a picture of clouds. And as we optimize, basically this network is figuring out what it sees in the clouds. And the more time you spend looking at this, the more things you also will see in the clouds. You can also use the face network to hallucinate into this, and you get some pretty crazy stuff. Or Mike has done some other experiments in which he takes that cloud image, hallucinates, zooms, and in this way you can get a sort of fugue state of the network, I suppose, or a sort of free association in which the network is eating its own tail. So every image is now the basis for what do I think I see next, what do I think I see next, what do I think I see next. I showed this for the first time in public to a group at a lecture in Seattle called Higher Education. This was right after marijuana was legalized in that part of the world. So I'd like to finish up quickly by just noting that this technology is not constrained. I've shown you purely visual examples because they're really fun to look at. It's not a purely visual technology. Our artist collaborator, Ross Goodwin, has done experiments involving a camera that takes a picture and then a computer in his backpack that writes a poem using neural networks based on the contents of the image. And that poetry neural network has been trained on a large corpus of 20th century poetry. And the poetry is, I think kind of not bad, actually. In closing, I think that per Michelangelo, I think he was right. Perception and creativity are very intimately connected. What we've just seen are neural networks that are entirely trained to discriminate or to recognize different things in the world, able to be run in reverse to generate. And one of the things that suggests to me is not only that Michelangelo really did see the sculpture in the blocks of stone, but that any creature, any being, any alien that is able to do perceptual acts of that sort is also able to create, because it's exactly the same machinery that is used in both cases. Also, I think that perception and creativity are by no means uniquely human. We start to have computer models that can do exactly these sorts of things, and that ought to be unsurprising. The brain is computational. And finally, computing began as an exercise in designing intelligent machinery. It was very much modeled after the idea of how could we make machines intelligent, and we finally are starting to fulfill now some of the promises of those early pioneers of Turing and von Neumann and McCulloch and Pitts. And I think that computing is not just about accounting or playing Candy Crush or something. From the beginning, we modeled them after our minds, and they give us both the ability to understand our own minds better and to extend them. Thank you very much.